Welcome everybody to the Johnson Matthey Platinum Group Metals Conference, Critical to the Future of Sustainable Technology. So what is the role of PGMs in the future technologies, or those technologies that are going to allow us to have a beautiful, sustainable and successful future as human beings on our wonderful planet? My name is Dr. Sarah Gordon. Now, before we get started, or basically the bit that you have all been waiting for, because of course this is a conference, and Emma, I'm going to invite you to maybe say some words against this particular slide, because of course this is a Johnson Matthey conference. There is a little bit of a legal disclaimer we need to flash up at the beginning in front of you. We will put this into chat as well if any of you want to read this in detail. So with that, I'm immediately going to welcome to our virtual stage the phenomenal Bruce Lipshutz. Bruce will be sharing his screen as I carry on speaking to fill this little gap, because you certainly don't want me speaking about the delights of cross-coupling chemistry. There's lots of alliteration that goes on in this space at the moment. It's fantastic. And so with no further ado, I'd invite you all, please put your hands together for the fabulous Bruce. Bruce, over to yourself.
Thank you guys so much. I really appreciate that and the opportunity to give this talk. I appreciate all the work that has gone on with Rose and Sarah and Emma. Obviously, this has been quite an ordeal, and I'm really honored to have this opportunity. I hope that I'm clear. I hope that my screen is available to everybody. I assume that I would be told if that wasn't true. So what I'm going to do is, I mean, Emma's already pretty much given half of my talk already, which is okay, but I'm going to spend a lot of time of the time I have available talking about, of course, platinum group metals, but in particular, palladium, and our view, at least, as to how this particular metal is so useful in terms of so many different applications that I think this is really important in looking towards the future. Now, part of what I was asked to do was sort of explain why palladium, why is this so important? I don't want to spend a lot of time, because I think a lot of people probably know this better than I do. But if you just look at the sort of electronic configuration, I think, you know, palladium is one of those things that it's sort of a Goldilocks phenomenon, right? It's perfect. It's right in a position to do the kinds of chemistry that we needed to do, at least for the intended purposes, which we will talk about. You can see that it's flanked by, yes, group 10 metals, nickel and platinum, but there's a lot of effort, as sort of Emma suggested, with these sort of earth abundant metals, and nickel in particular, which a lot of people, myself included, look as sort of a wannabe palladium. And yet, if you look at the electronic configuration, yes, you can get there in terms of oxidative addition and all that, but the reality is palladium is just perfectly positioned to do this kinds of chemistry. So that being said, why do we spend so much time? Why are there so many people thinking about nickel chemistry and trying to get rid of the platinum group metals and move this to base metal catalysis? I think this is the wrong approach, and I'll show you one that actually works. So part of the problem with going to things like nickel to try to replace palladium is it isn't there yet. People use too much of this. 5% is very common. That's way too much. We're only talking about 1920 turnovers. It's barely catalysis. Chemistry today is unfortunately done in organic solvents, tremendous waste generation, burning, CO2. I don't have to tell you the implications of that. Energy involvement, we're going to talk briefly about that. We all, especially Europeans, understand the implications of that. We'll talk, as I say, more. Functional group compatibility, high temperatures, right? It just doesn't help the situation. And then what about if you're looking at making drugs? The FDA puts a limit, roughly 20 parts per million per nickel. I can guarantee you, if you're using 5 mol%, you've got a problem. And now you have to pay time and effort, create more waste. It's not environmentally respectful. It's a big problem. And then, of course, we have efficiency, not as good as palladium. And now let's talk about ligands. And palladium has hundreds of different ligands that have been developed over time. Nickel just isn't there. So from the standpoint of trying to replace palladium with nickel, I just don't see that happening. Maybe at some point in the future. Most people are looking to do these cross-coupling reactions. This is not to say that nickel doesn't have its place, as you can see from the screen. Yes, it has very exciting possibilities, nickel 1, nickel 3, different kinds of coupling reactions, photocatalysis, etc. It has its place. That chemistry is spectacular, but as a wannabe replacement for palladium, I don't think so. There's better ways to do this because we know how to use palladium. Then comes the endangered metal status. Is not for me. This is the Green Chemistry Institute saying, hey guys, we have a problem in terms of long-term endangered elements. And that even includes, right, the so-called earth abundant metals, cobalt, nickel, copper. But from the standpoint of PGMs, you can see that long-term we have to be concerned, even as Emma pointed out, we have more coming, right, in the short term. What exactly is happening long term? And then comes the price situation, which a lot of people focus on. They point to the Aldrich catalog and they say, look at the difference between nickel and palladium. Well, that's again a very short term sort of perspective. It's also not right. But that being said, look at the graph. I mean, it's self-explanatory. You know, if we could do this chemistry with less palladium, then of course the pricing doesn't really translate into something we have to worry about. How much time do we have left in terms of access to palladium? I don't know. Do we have 50 years, 100 years? But let's just pick a number. Say it's 100 years. If we could figure out how to do what we already know how to do with palladium, but use less of it, maybe 10 times less, well, moving the decimal means that those, let's say 100 years become 1,000 years. And to me, that's a solved problem. We have to look long-term. We have to make sure, as we will see from the standpoint of the fine chemical industry, that we have palladium available for its use because it is a special metal, because it is the king, as we will see. Now, it was mentioned that we have more in the short term, certainly palladium coming on board because of the catalytic converter stuff. There's no doubt about that, but to balance some of that, let's appreciate, maybe this was said this morning, and I wasn't part of that. I was trying to get some sleep, but the bottom line is that the world's largest mine for palladium is Russia. So what do geopolitical issues mean in the short term, especially? I don't know exactly, but it sounds to me like this could be a problem. You know, good luck getting palladium from Russia these days. So yes, we have material coming online, but this sort of balances that to some extent. So is it surprising, I mean, as Emma pointed out, that you guys expect, all right, that the shortage is going to start to go away in 2023 for the catalytic converter issue? Absolutely. But that does not mean, as Emma pointed out, and this is the first page of her perspective that she commented on, it doesn't mean that this is the time to ignore, right, the overall long-term perspective. Now's the time, as we will see from her conclusion, right, is the time to pay attention, not just to the short-term issues of availability, but also how do we use it in the long term? And so what are the markets? You guys, again, know this better than I do. Our interest is mainly from the standpoint of fine chemicals. Why? Because the pharmaceutical industry, which I include as part of that group, obviously makes the medicines that keep people alive. The agrochemical industry. We have to be able to feed the planet. Palladium is used, flavors and fragrances. Absolutely the king, as is pointed out in this Roger Sheldon and co-worker book on green chemistry. We have to pay attention to how we use, develop the new technologies. And the problem with this industry, as again, Roger Sheldon points out, is waste. We are, unfortunately, in modern organic chemistry, based on petroleum. For 200 years, we have looked at ways of using organic solvents and particulates. We'll see. And this is, again, not me. This is Roger Sheldon saying, hey, look, we have a problem here because without even including the water, just based on the organic solvent, we're creating 25 to 100 kilos of waste for every kilo of drug. This is not sustainable. There's no way that this continues. We have already polluted the heck out of the planet. We have to do something about that, because the fact of the matter is water is also included. And again, this is not me, but we have to appreciate the gorilla in the room here is the organic solvents. If you take the water out, okay, you're at over 80% right away. Should we include the water? Yes, we should, because think about how reactions are worked up. You dump it into water, and what happens to that water? It's not pristine. Salts, starting materials, products, catalysts, we dump it. That's close to 90% of how we do chemistry, and that just cannot continue. So when we do palladium-catalyzed reactions, we oftentimes heat reactions. Let's just talk about energy. Huge. I don't have to tell you in Europe the prices. And what's the problem with using the energy, investing it, aside from the cost, is the 100% yield problem. We know and appreciate the activation energies associated with reactions, but these reactions give side products and purity profiles, and then we have to purify, spend more time and effort, chromatography, waste generation. And quite frankly, I cannot identify the last time that nature ran a reaction in reflux and toluene. Nature doesn't do that. Why do we create these problems? So one solution to that is to look to nature and to use what I would call sort of dirty water, meaning let's put things in the water that enable us to do chemistry like biochemistry. There's no question we understand biology and biochemistry evolved and currently use water as the medium. Let's figure out how to do that. So we came up with a workhorse surfactant, call it what you want in terms of, there's lots of names, right? For surfactants, detergents, emulsifying agents, et cetera. It doesn't matter. TBGS, we use it. We want it to be benign, meaning it's based on vitamin E. And I'm going to say this, don't do what I'm about to tell you. But the reality is when these go into water and you run your reaction in water, which is taking place inside these micelles that these surfactants are going to form, when you're done, if you get everything out, you could drink the water, because this is just like an ester E, right? This is nothing more than going to be broken down and supplying vitamin E. So these are benign. And then we wanted to deal with PEG because PEG isn't metabolized. PEG is sort of forever. People had a problem with that. We came up with a biodegradable replacement, drop-in replacement, which we call SAVI. And you'll notice that now we have just a polypeptide, which is just sarcosine, right? I mean, it's just N-methylglycine, and that works very well. So when these come together, these designer surfactants, right? This is the key to using chemistry in water. They form these micelles, which are nanoreactors. Nothing is soluble in the water. We're going to use very little of it to weight percent, right? To weight percent, and the molecules weigh over 1,200, so it's hardly any in there. And we're going to run reactions 0.5 to 1.5 molar in water. So there's very little water in there and nothing soluble in the water. So everything wants to go inside the micelle. So how do we run reactions at room temperature? Because the analogy is, let's say an elevator. It holds 50 people, but you shove 500 people because we're 10 times the normal concentrations in organic solvents. You shove 500 people in that elevator. Honestly, there's going to be a lot of chemistry happening in that elevator. That's exactly what happens in a micelle. The substrates and the catalysts all compete. They want to go inside. The chemistry happens. You don't have to heat these things. Think about yourself in an elevator. You move an elbow. Somebody's going, what the hell are you doing? That hurt. It's the same thing in the micelle. It's over 2 molar. So that solves the energy problem. And then, right, everything is competing to get in there. So you look at this and, we have not sort of developed anything new here. This is something that's been going on for 1 billion years. That's how nature does its chemistry. That's how we survive, because we are not totally in water. What happens to all the molecules in the human body that are not soluble in water? The vitamins, the CoQ, the polypeptides. Nature figured all this out 1 billion years ago. They're in the vesicles, the membranes, the micelles. Okay, let's follow nature's lead and think about the water that was, here for a billion years. It wasn't pristine. So let's make these things. Now we're going to engineer them. They're going to be modern, but look at all the chemistry that we can do. There's no relationship between palladium catalyzed reactions and ruthenium and copper, etc. They all work because these are, in a sense, sort of like brain dead enzymes. So things go inside because nothing's soluble in water, the chemistry happens, and now we can do all kinds of things. And of course, right, Nobel Prize winning, this again is not me, the study was done, Suzuki couplings, #1 in terms of using palladium. It's the only one that sort of made the cut. Palladium chemistry, this is a lot of where the action is. So we have designed ways of using less. Let's just think about doing more chemistry with less palladium. And so we want to do chemistry that we already know how to do, but with 10 times less of palladium, so that 100 years becomes 1,000 years. So your children and my children and grandchildren have access to the medicines, we can feed the planet, etc. This is why we're doing what we're doing. And of course, there's very little, if any, organic solvent in this chemistry, and it has to be applicable to real molecules. Lots of nitrogen and heteroatoms. All this chemistry has to work in a way that a pharmaceutical chemist, a discovery person, a process chemist would be attracted to this chemistry. So here are just some examples. You can see there's kind of real molecules. SABI works very well as a replacement for TPGS because of the biodegradability. Look, and you see 2,500 ppm. Well, that's 0.25 mole percent. Where is the 1 to 5 mole percent that everybody's using looking towards the future? We just can't do that. Now is the time to develop this chemistry, to replace the petroleum, leave it in the ground, and use nature's chosen reaction medium, which is water. And so you'll see palladium at 1,000 ppm, that's 0.1 mole percent. This is sort of unheard of, but now you understand better the goal. And to do this, the secret to this chemistry is, again, to think about that elevator. If, based on binding constants, we can ligate the palladium and have it go inside that elevator and stay there, then we need less of it. And that's the secret. So you see, we developed our own ligands. They don't exist. We had to develop them specifically for use in water, specifically to go inside those micelles, specifically to enable this chemistry to take place at the ppm level of palladium, extending its lifetime. And when you do that, it works. That's the key. So we also appreciate that industry loves heterogeneous catalysis. Why? Because you just filter things and it's easy to separate the palladium catalyst. We also have developed nanoparticles, as shown here, from dirt cheap ferric trichloride. We just mix all this together with a Grignard, we make these nanoparticles, and now it's kind of like surfing the web. What chemistry do you want to do? So you add ppm level of palladium and the ligand, which controls the type of chemistry, and now you can do chemistry with very little palladium. 0.05 mole percent is all you need to do this chemistry. 200, so this is 100 times less than one would typically use in that 1 to 5 mole percent category. So I don't want to spend time on these examples. You know, this is recently published, but the bottom line is 500 parts per million, 0.05 mole percent is all it takes under very mild conditions to get this chemistry to happen. That's how we are going to enable palladium to be around forever. Now, do other kinds of couplings work? Of course they do. I'm not going to take your time to talk about Negishi couplings, etc. Okay, they're Nobel Prize winning, but the point is the concept applies. I think you could imagine how one could extend this just by varying the ligand for the name reaction. That's so important. So the final kind of comment I want to make is about CN bond forming reactions. Very important in terms of especially pharma and ag. Again, we're focused on this. And as you can see, sort of going to the left at the top of the slide in red, it's not uncommon to use 1 to 10 mole% palladium to do this chemistry. It's just like out of the question, not sustainable, going nowhere, can't be scaled up cost-wise. It just makes no sense. And you see relatively few examples. But suppose we could cut that palladium, again, tenfold. So we have developed technology to enable us to use 0.25 mole% of palladium, ppm levels of palladium. What's the secret here? Again, look at the ligand on the right-hand side, the palladium-containing precursor. You see that allyl group, it's cinnamyl, because it's got the phenyl group on the right. So it's the cinnamyl precursor. This is not by coincidence. Again, remember the idea of getting that catalyst inside that elevator and staying there. If you take that phenyl group off and replace it with a methyl, rhodal, doesn't work as well. Take the methyl group off, simple allyl, doesn't work as well. It's by design. And once you know nature's rules, these problems can be solved. This enables us to do this chemistry, these amination reactions at the ppm level. Can we use nanoparticles, for example, to do this chemistry? Absolutely. And so as you can see, we're in 0.25, 0.35, but as you will also see associated with this chemistry, because it's nanoparticles, right? We can do aromatic amines, we can do aliphatic amines. Very tough to do chemistry. And you could say, well, wait a minute, you know, you're up to 5,000, that's 0.5 mole%. Yes, but you're forgetting we're in water. And when these reactions are over, right, we can recycle, and we recycle everything. So for example, you could say 5,000 ppm to start, but the first recycle only takes another 2,000. The next one takes 2,000. The third one takes 1,000. You add them all up and you get 1 mole%, but it's over 4 reactions. That's 0.25 mole% for an amination reaction with an aliphatic amine. Absolutely unprecedented. But again, the point is, think about the palladium long-term. We get it forever using this chemistry. So Emma, I'm going to use your conclusion from your sort of perspective, because it's right on the money in the sense that it's telling us, look, okay, we're going to have palladium for a while, but now's the time to develop this chemistry so we have it long-term, forever. And now is the time to develop this chemistry, which is sustainable for the future. So again, this is the article in which I showed you previously. I would encourage you to see this. So let me just summarize, leave some time for questions here. This is what I've been trying to get across, is that this is not new. We are proof of the following sort of chemistry, which we're just modernizing, right? We're just taking nature's concepts of using places to do the chemistry in vesicles, and now we're modernizing that. Okay, we have this surfactant, it's easy to, you know, it's cheap, blah, blah, blah. But the point is, it enables us to get the loadings of the platinum group metal using palladium in particular, so that it's here long-term. We can do that chemistry in water. We don't need organic solvents anymore. We need to get away from those and just follow nature's lead. We can do that. We can get the temperatures down. We don't need to invest energy. Let room temperature condition. Now that varies all over the world. Sometimes it's 20 degrees, sometimes it might be 45 degrees or even 50 with climate change. But the point is, let's just use the energy that's given by nature. Let's appreciate that there are limits to what we can tolerate, but I can assure you that if you use ppm level palladium catalysis, you don't have a problem. The loadings, as I showed, I didn't point this out, in terms of using that level of palladium, you don't exceed the 10 ppm limit imposed per dose per day by the FDA. Another benefit of doing this chemistry in water. Why would the palladium go into the water and contaminate the product? It's not soluble, it stays home because we design the ligands to keep it there. And now come, I think, what is the future of organic chemistry is to combine biocatalysis, enzyme-based catalysis with chemical catalysis, because we can do everything in water. Of course, enzymes are most productive in water. We have the chemistry in water. So we just end up doing both in one pot 2 steps, 3 steps, 4 steps. We keep going. Why would we work a reaction up to put it back into the water? We don't. So all of this technology is here today. We're putting a lot of tools in the toolbox. I have some great students that have done this work. I want to thank the funding agencies, the companies mainly in particular, that see the future, that have the vision, share the passion, and want to keep the metal use to a minimum for a variety of reasons. Of course, it's economics, but also it's to make it available for the future. So thank you all again for listening and for the invitation, and I'm more than happy to answer questions.
Brilliant. Thank you so, so much, Bruce. Massive round of applause from all of us who are listening in. That was truly fantastic. And I have certainly learned a lot in the last few minutes. I also know that Emma has been blushing greatly, seeing as you kept citing her work, which is glorious.
It's true. It's
and
true.
there has to be an opportunity to counter-cite, because Bruce and I wrote a perspective each in that particular journal. They're back to back, and I've put the links for them in the chat. Well worth, it's always worth reading, Bruce, but well worth reading both of those.
Well done, Emma. Fantastic. So Bruce, I guess to translate that into very much layman terms, number one, palladium is awesome, especially if you get stuck in a lift with it. Number two, nickel is just rubbish. So you do not want to get stuck with the whole nickel thing. And because palladium is so awesome, actually having the opportunity to work out how to do more with less palladium is what we're after. Am I correct?
Yes, and the enabling technology, meaning that enables one to use the palladium at such low levels, is really nature's secrets, which we are discovering. It's really about finding out how nature allows us to do that. If we tried to do that in organic solvent, it just doesn't work. I mean, ligands and catalysts were not designed to do chemistry in water at high concentrations, exchange phenomena, things that are happening, binding constants that there's no way to put it. When you're in solution, you're in solution. So it's really about nature. It's really discovering the secrets that are there. Nature's laughing at us like, what took you so long to figure all this out? It's been there. We just have been like horses with blinders, sort of just based on petroleum. We need to get off of this. And nature is finally saying, well, it's about time. But yes, it's a combination is what I'm saying. It's not just using less palladium. It's enabling us to use less palladium that is crucial. And that just is, to me, very obvious. I mean, this is the benefit of following nature. I mean, you know, you have on one hand 200 years of modern organic chemistry in petroleum and 1 billion years of nature doing chemistry in water. Who are you going to bet on? I'm betting, obviously, on nature.
I'm going to slide a word in here, because I'm the person who's obliged to be more diplomatic on this call. And I would qualify the fact that nickel is rubbish. I would say that nickel is good for what nickel's good for, but palladium is good for what palladium's good for, and don't try and mix the two.
Fantastic. Thank you, Emma, for correcting me there. Brilliant. Now we've got a couple of questions that have come in, Bruce, if I may. So the first one that came in earlier on was from Mike. And Mike was asking what quantity of palladium is used for the cross-coupling worldwide, and what could it grow to over what time scale? So I guess we're asking how much.
Yeah, you know, that's a good question for Emma. I'm just a chemistry professor. I don't really know how much palladium is used. I think the question is, how much palladium do we use worldwide to do these cross couplings? There's them and there's us, of course. They're using 10 times more than we do, but I don't have a number as an academician. I don't know, Emma, do you have a feeling for how much palladium is needed by pharma and ag? Ag, of course, is 10 times more than pharma, but that doesn't mean I know the answer.
So I did the back of the envelope as you were talking. I took the number 292 tons for the whole chemical sector used in up to 2022, of which I know that 6% is used in the chemical sector, which is 17.5 tons. But of course, cross-coupling is a subset of that. And I'm doing it in tons and not ounces for the benefit of our less familiar audience.
Yeah, so I hope that answers the question, but only Emma, well, Emma's the right person to ask.
Just as well, we've got all the right people on the call, isn't it, Bruce?
Yes.
I've got we've got time for just one more question before we move across to Axel and we get to hear about this amazing thing called spintronics. And this question comes in from Detlef, and Detlef was asking, is it complicated to separate the products from the micelles? So do you want to talk about that?
Yeah, actually, it's one of those secrets of nature. I mean, let's face it. What I haven't told you is the dynamics associated with micelles. They're not golf balls. They're very promiscuous. The surfactants are moving between themselves. Everything is on the state of sort of flux on the NMR timescale. So that includes the products. So as the products are formed molecule by molecule, they're exchanging between the micelles through the water. Well, they find each other. When they find each other, what do? They drop out because nothing's soluble in water. So what I'm telling you is there is no workup. If you're dealing with a solid in pharma, especially, which is only for the most part in solids, the whole thing is just filter. You just filter to get your product. And what do you do with everything else? The filtrate, the water, the surfactant, even the catalyst, you recycle it. So the bottom line is no waste. It's really that easy. It's a beautiful thing because you're in water.
All about swimming around in that water. Brilliant. Thank you so much, Bruce. There are some other questions that are coming in for you, but if I can invite everyone to please put your hands together for the fabulous Bruce.
Thank you so much.